substituted in terms of sigma x, sigma y, you don't see any sigma z. And sigma z is taken care of this factor k. This is called corrosive coefficient, this is kappa. So kappa is, so this parameter will always encounter in factor mechanics in our lecture. So kappa equals 3 minus 4 nu for plane strain problem, 3 minus nu by 1.0 for plane stress. So if you substitute kappa as 3 minus 4 nu here, you will get a strain energy density for plane strain. If you substitute kappa 3 minus nu by 1.0, you will get strain energy for plane stress problem. Okay. So this is in general calculation of strain energy density at a point. Now, how then G can be calculated from experiment? Okay. So we will talk about the experimental method as well as the numerical method. So suppose you have load. Suppose you have a component shown here. Okay, that is the crack length A, and you are applying some force or displacement. Okay. So we will see both. One is where applying the load, other where applying the displacement. So that is called load control and displacement control. These are very important concepts we will be talking. And this component is fixed here, that specimen is fixed here one side and you are pulling it. Okay, it is in tension. So what will happen? Suppose if there is no, let us say, material is elastic, what will happen? Force and F is the force in y-axis, U is the displacement. So as we apply more and more force, you will get more displacement. It is in material is linear elastic, so you will get a straight line. Okay, linear elastic material. Now, you know that after when force reaches some critical value, because here the stress, if you convert the force into stress, nominal stress, so there will be some sigma critical, and there is a crack is there of the material. So sigma critical in root over pi A1 initial crack line. So then the crack that is condition for crack to propagate. So then crack will propagate. Now once crack propagates, so then you can see the load will start reducing. Okay, so now you can see then here for crack A2 we have a the point is here. Then load then further if you go up means when crack is propagating, okay, then load is reduced. Okay, then here what I am telling basically I am applying a displacement control. Okay, because load if I use a load control problem, if I increase the load, then here it will become unstable. It will just fail here. Okay, its cord will not go down. You must understand this is very important. So what I am doing is actually I am applying a displacement. Okay. So up to here, so it is linear elastic. Then after that, the load is reducing, the crack is increasing. Okay. So you are applying a displacement to the displacement. Okay. You are just fixing it and pulling it by certain displacement. So as you go on increasing the displacement, the load is go on reducing. Okay. And when it will go to zero, when this crack will propagate fully, so it becomes too fast. Okay. So now, in case of load control, it will stop here. Means it is just the displacement becomes similarly go horizontally, it will become infinite. It will just break into two parts. Okay. So this is the difference you can say for load control control. Now, so Griffith told that we can calculate this by the following method. So suppose you want to calculate the energy release rate, or you can say resistance. Here at resistance G at crack length A3. Okay, that means from A3 to A4, how much energy is released? So this shaded area is energy release when crack is propagating from A3 to A4. So that is nothing but the shaded area under low displacement is the total energy divided by the B thickness into A4 minus A3 is crack length. So the product of B and this is crack length delta A, how much increase? That is nothing but area, the crack additional area that is created. So the energy, numerator is the total energy that is released divided by the area. This is natural energy released at point A3. So similarly here from A1 to N2, this area will be the energy released rate. A2, A3, this area. So you can see that the resistance, okay, whether they remain constant or increase that you can get from this area. Okay, this is one of the very beautiful method to calculate from experiment. Okay, and then once you know the G, then you can always convert to K1 square by E. Okay, so where you can the K1 the expression you can also derive for a given geometry. So this is one of the experimental methods in which you can evaluate the stress index factor or G. Both are equivalent because G is related to K by K1 square by E. Okay, I will just take another 5-10 minutes, 5 minutes to before I stop for today. So to more elaborate it, so as I told, there are two ways we can load this specimen. Either we can use the displacement control or I can use the load control. So the first case I am talking is, so the according to Griffith, G is nothing but minus d pi by dA. That is the pi is the potential energy, and with area per unit area. And why is negative? Because it is release energy that is released into system is negative. Okay, that's why the negative sign is there. So here we are talking about the fixed drift. Fixed drift means you just load displacement, that is the crack, and you just pull it to certain displacement u. Okay, then what will happen? So initially the crack length A1, this line. So once it reaches some value, then and you are fixing the grip, means you are not increasing the displacement further, but crack will propagate because it has reached the critical value. Then automatically the load is reduced. Okay, because crack has propagated, and it will stop at certain point where because this point the energy release rate will be less than K1C. Okay, so here it is exceeding K1C, it will become less than. So here crack will propagate this much. So this is A1 is initial crack, total crack, final crack A2. So A1 plus delta A. So for crack to increase from A1 to A1 plus delta A, that is additional amount of delta A, this much energy has been released. Okay, so this so how do you do it? You just fix bottom side, and top side you put a screw, and suppose you pull it by certain amount, and you fix it. Don't go on pulling it. Okay, so this is called the fixed drift. Okay, so this anybody can do the experiment for a material that is special for brittle material. So what then according to energy Griffith concept, so this area that is OAB, that is nothing but energy that has been released. So so that is the potential energy nothing but UE strain energy minus work done. So let us calculate both strain energy and work done. What is strain energy? So initially how much energy you are given, that is area OA, and suppose this is C is the bottom of OAC. So it's nothing but T1, so this is 0 AC, and then energy that is after the crack has propagated is OBC. C is the and the bottom here. Okay. So the difference in energy delta U, the strain energy, is nothing but minus half P1 minus P2 by U. Okay. And what is work done by forces? Because here there is a fixed drift, U is not there, so you know the work done is always F into delta U integral. Okay, so the delta U is 0. So for fixed drift, the work done is 0. External work is done 0 for this case. So now G becomes nothing but so pi potential energy is nothing but UE. So G becomes minus UE divided by A. And what is area? Area means how much area is created. So that's the product of thickness in delta A. So you could divide by thickness in delta A. So G becomes 1 by B delta A into half P1 minus P2 U. It is nothing but 1 by B area OAB by delta A. Okay. So this is the so OAB can always estimate. This is one of the methods for the fixed drift. So tomorrow we'll talk about in case of fixed load. That means suppose I put a load.
Sir. Sir, work done is equal to 0.
Work done is 0 because there is no displacement change. So when you go to P1 to P2, that point A to B, how much is the change in displacement? 0, right? Because I am not changing the displacement, of grip is fixed. Okay, this is called fixed grip condition. Okay, so you see I have initially loaded given some what that is stored as a potential energy. I am calculating from A to B how much is the change in potential energy. That is how much change is strain energy, how much change in the work done. How much change in strain energy is there? Strain energy is nothing but sigma, half sigma into E. So if you see the difference, that is area OAB. And how much work is being done during the process of crack growth? So during the process of crack growth, there is no change in displacement. Okay, so what is work done? That is force into F dx integral, right? So dx is change in displacement. So that dx is 0. Okay, so for fixed grip case, that work done is 0, delta W, that is change from A to B. So
displacement of crack.
Is not crack. Displacement of body. You see this geometry. What I am doing is this is called CT, compact tension specimen geometry. Okay, the kind of you take a square, the rectangular geometry, make a crack, and it has some thickness. And here in the pin you just put you pull the pin to some displacement. Let us say you pull it to 2 mm. Okay, and leave it. Okay, you fix it. If you don't go on putting the your displacement.
Then displacement is okay.
Yeah, it is. So here you can see fixed grip. Okay, So you just pull zip to 2 mm and fix it. So the crack has propagated. So during time crack propagates, what you are telling, when that is crack is propagating, how much work is being done? So work being done is zero. And how much strain energy is done? Strain energy is being released because strain energy which is already stored, it has reduced because of crack propagation. Okay, so that strain energy is nothing but P1 minus P2 into U by 2. And work done is zero. Yes, so area under that OAB. So total potential energy is nothing but area of OAB, and potential energy release rate, that is per unit area, that is divided by B into delta. Is it clear? So for fixed load we'll talk tomorrow. Okay. So we'll see that both expressions will be same. So now what we'll do? So here we'll be discussing method to evaluate G. Now later we'll connect G to the stress intensity factor, and then we'll talk about concept of the plastic plastic zone size, how to correct for effective crack length. Okay, and all these are in the within the domain of linear elastic fracture mechanics, that is extended domain. Later we'll see that the linear elastic fracture mechanics concept will not be applicable when there is a lot of plastic deformation. When the plastic deformation exceeds certain magnitude, then you have to go to concept of JNT car. Okay, so those in this line will be covering our the portion of the fracture mechanics. So is it clear to you?
Yes, sir.
Okay, so this slide I will send to you. Okay, so you go through this. So tomorrow we will again meet 11:30 12:30, and this Saturday also we have class. So that is 8:30. We have the C class. So I have to take it lecture because it will be to maintain continuity. But total number of lectures will be fixed. I will take only 13 lectures. Okay. So towards the end, I will make the lecture. I will not take. So this Saturday, wherever there is a C class is there, 8:30 to 9:30. That is a calendar. It is free. So you keep it for this fracture mechanics class. So other day, Tuesday to Saturday, we will taking 11:30 to 12:30. And Saturday will take additional class 8:30 to 9:30. For this is an additional class. This is the class which I am pre-coning. Okay. Later I will be not taking those classes. So it is only to make it because when you are covering, in fact, the fracture mechanics lecture could be, if you do it, together it will be better because certain concepts while explaining you take more time. Is it okay with you, people? Hello?
Yes. Yes, sir. Yes, sir.
Okay. So tomorrow also.
Thank you, sir.
Okay. So this link, this Google Meet link is same. It is valid for tomorrow also. Okay.
Okay.
Tomorrow also is